Somewhere 15 billion miles from here, a machine that has not changed direction in years just moved. And what it sent back afterward is the reason a handful of NASA engineers have spent the last few days quietly rechecking the same data over and over, trying to figure out whether what they are looking at is real. The spacecraft in question is not new. It carries no modern sensors, no updated processors, nothing built after the disco era. It is the same hardware launched in 1977, running today on a fraction of its original power. And for a brief moment, after nearly 50 years locked in a single fixed position, it rotated and returned a reading that does not sit comfortably inside any current model of the space it is flying through. This is Voyager 1's story, again, because it refuses to stop being one. By the end of this video, you will understand exactly why turning an ancient, dying spacecraft just a few degrees off course has become one of the most quietly significant events at JPL this year. I'm your name, and this is your channel. Hit subscribe if you want more of these, because there's plenty more where this came from. First, some context on why this rotation was such a big deal in the first place. Voyager 1 left Earth on September 5th, 1977 on a mission built to last roughly 4 years. Fly by Jupiter, fly by Saturn, snap some photos, and go quiet somewhere around 1981. It never went quiet. It used the gravity of both giant planets to slingshot itself further and faster than anyone planned, and it just kept going. By 2012, 35 years after launch, it crossed the heliopause, the boundary marking the outer edge of the sun's influence, and became the first human-made object to leave the solar system entirely and enter true interstellar space. It has been transmitting from out there ever since, its signal taking more than 22 hours to reach Earth, even moving at the speed of light. For nearly all of that time in interstellar space, Voyager 1 has held one single fixed orientation, its antenna locked on Earth, KEPTA, steady by a small set of aging thrusters firing in careful, minimal pulses. Actually, rotating the spacecraft away from that locked position has always been one of the most dangerous requests engineers can make of it, because there is no backup plan if the antenna fails to reacquire Earth afterward. Every degree of movement risks permanent silence. Every thruster firing spends fuel that will never be replenished. That's the backdrop for why a scheduled roll maneuver on Voyager 1 recently was treated as such a serious event inside Mission Control. It was part of the broader thruster testing work tied to the power management procedure engineers have been quietly running throughout 2026, an effort aimed at stretching whatever operational life remains in a spacecraft that is slowly losing electricity year by year. A similar version of this procedure had already been tested successfully on Voyager 2 earlier in the year, since it has a bit more available power and sits somewhat nearer to Earth. The plan for Voyager 1 itself was meant to be simple. A short, precisely calculated rotation to test how the aging thrusters responded, and to briefly shift the angle of instruments that had not moved in years. On paper, it was routine maintenance, the kind of task that quietly disappears into a mission log nobody outside JPL ever reads. It did not stay routine for long. During the short window when Voyager 1 was off its usual orientation, before the antenna and instruments swung back to lock onto Earth, several of the spacecraft's remaining working systems picked up something unfamiliar. Engineers are still double-checking the specifics, but early data from the magnetometer and the plasma wave subsystem, two of the few instruments still active on Voyager 1's shrinking power supply, showed a sudden, tightly defined deviation unlike anything recorded in the background readings since the spacecraft entered interstellar space back in 2012. This wasn't the familiar, slow drift of the persistent, unexplained hum the plasma wave instrument has quietly been picking up since 2017. It was sharper and much shorter, a distinct spike lasting only a matter of minutes, appearing almost exactly as the spacecraft's orientation shifted, and fading out again once the antenna locked back onto Earth. The engineer's first assumption, and the correct scientific instinct, was that this was simply an artifact of the maneuver itself. Rotating a spacecraft can produce all sorts of misleading signals. Thermal changes as components shift in and out of direct sunlight, electrical noise from the thrusters firing, brief stress on circuitry that has nothing to do with the outside environment and everything to do with the machine's own movement. That explanation gets ruled out first because it is usually correct. So the team cross-referenced the anomaly against the exact timing of every individual thruster pulse fired during the roll. They compared it against noise patterns from Voyager 1's very few previous maneuvers of this kind. They checked whether anything similar had ever shown up during the tiny, routine attitude corrections the spacecraft performs constantly just to keep its antenna steady on Earth. None of it matched. The structure of this particular signal was different from anything the thrusters alone had ever produced before, and that is the exact moment a quiet maintenance log entry turned into something the mission team is still working to understand. Here's what actually makes this different from just being a dramatic headline. Since 2017, Voyager 1's plasma wave instrument has been picking up a faint, continuous signal in interstellar space. one that researchers have described in published, peer-reviewed research as clear evidence that the region between the stars is more turbulent and structured than any existing model predicted. That background signal has been nearly constant, present in almost every reading the spacecraft has sent home for close to a decade. What appeared during this roll was not simply more of that same hum. It was a distinct spike layered directly on top of it, tied precisely to the exact moment the spacecraft's angle relative to the surrounding interstellar medium changed. At the moment, there are only two physical explanations being seriously discussed among the small group of researchers reviewing this, and neither has been confirmed. The first, and the one most engineers currently favor because it doesn't require rewriting existing physics, is that the rotation simply changed the angle at which the instruments were sampling the surrounding plasma and magnetic environment, revealing that this particular pocket of interstellar space is far more directionally uneven than previously understood. Under this reading, Voyager 1 didn't stumble onto something brand new so much as it accidentally proved that the turbulence already suspected out there has real shape and direction, something a spacecraft frozen in one orientation for 50 years could never have shown us. Even under this more conservative interpretation, the implications matter, because it would mean a decade of models built from Voyager 1's steady single-angle data may have missed an entire dimension of structure simply because nobody ever turned the instruments far enough to see it. The second explanation is the one quietly dividing opinion among the handful of scientists who work closely with this data. Some of the readings from the roll are harder to explain as a simple change in sampling angle. A few researchers, speaking carefully, have noted that the magnetometer's pattern during that brief window looks more like a small, localized disturbance in the magnetic field immediately surrounding the spacecraft, rather than a new vantage point on an already known, broader environment. If that interpretation holds, it would mean Voyager 1 didn't just get a better look at familiar turbulence. It would mean it briefly brushed against something localized and structured that has been sitting there all along. Small enough that a spacecraft locked in a single direction for years could have flown right past it undetected. And it was only caught because the timing of this particular roll happened to line up exactly right. Neither explanation is confirmed, and both are currently treated strictly as working theories by a small team who understand better than most how easily an instrument artifact gets mistaken for a genuine discovery, and how much damage a premature announcement could do to the credibility of one of the most valuable missions humanity has ever run. That level of restraint tells you something. The people closest to the raw numbers are not racing toward a dramatic headline. They are the most reluctant to say anything final, precisely because they understand exactly what is at stake if they get it wrong. It helps to sit with just how unforgiving these conditions really are. There is no lab down the hall to rerun this test in. No technician can be sent out to check the hardware in person. Every command sent to Voyager 1 takes more than 22 hours to arrive, and any response takes another 22 hours to travel back. A mistaken conclusion published too soon doesn't get quietly corrected the way it might at a university. It becomes a permanent part of the scientific record for a spacecraft that will never fly again, studied by researchers for decades after everyone working on this mission today has retired. The caution being shown right now isn't hesitation from doubt. It's precision, built from the knowledge that this data may be the only chance anyone ever gets to look at this exact question. There's an irony worth noticing here, too. Voyager 1's instruments were never built with anything like this in mind. They were designed in the early 1970s to study the magnetic fields and charged particles surrounding Jupiter and Saturn, planets that were themselves still largely unmapped at the time. Nobody who built this spacecraft imagined it would still be functioning 50 years later, deep in the space between stars, using a routine maintenance role to accidentally graze a piece of physics that didn't even have a name yet. The hardware was never upgraded. It was never redesigned for these conditions. It's the exact same electronics, assembled by engineers who couldn't have pictured the internet, let alone interstellar plasma physics, as an active area of research. And here it is in 2026, quietly sending back a signal that today's most advanced modeling still can't fully explain. Here's why this matters beyond the raw numbers themselves. Voyager 1 is running out of time. Its plutonium power source loses a small, steady amount of output every year, and the mission team has already been forced to permanently shut down 7 of its original 10 scientific instruments just to keep the spacecraft functioning and connected to Earth. The low-energy charged particle instrument, one of the few still able to directly sample the plasma environment, was switched off earlier this year, not because it failed, but because there simply wasn't enough power left to run it. Every reading Voyager 1 still manages to send home is now one of a shrinking, irreplaceable set of final glimpses into a region of the universe nothing else has ever directly touched. No mission currently exists, or is even funded, to replace it. Even a brand new interstellar probe approved and built starting right now would need at least 25 years just to reach the boundary Voyager 1 crossed back in 2012. whatever does or doesn't get confirmed. About this anomaly in the months ahead may be one of the last real chances anyone alive today has to look into it directly. None of this is happening in a vacuum either. This roll maneuver was part of the same, larger, high-stakes engineering effort currently underway to keep Voyager 1 alive at all. After the mission nearly ended for good in 2023, when a single deteriorated memory chip corrupted the spacecraft's data for 5 straight months before engineers painstakingly repaired it from 15 billion miles away. And after a year, spent carefully testing a risky power redistribution procedure first on Voyager 2, before cautiously attempting it on Voyager 1 itself. This maneuver was just one small piece of a much bigger fight to keep the spacecraft breathing. In other words, nobody set out to find this. It surfaced as a side effect of engineers simply trying to buy a little more time for a 50-year-old machine. And in doing so, they may have stumbled onto something the mission was never actually designed to look for. The team is reportedly preparing a second, more carefully instrumented attempt at the same maneuver, hoping to capture cleaner data if the same signature shows up again. There's no guarantee it will. There's no guarantee Voyager 1 has enough remaining fuel or power to safely attempt many more of these rolls at all. Every rotation carries genuine risk on a spacecraft that can never be serviced or physically reached again. The team is fully aware of this, and they are choosing to try anyway, because leaving a signal like this uninvestigated, purely because investigating it is risky, isn't something anyone at JPL is willing to accept while the spacecraft can still answer. This is exactly where humanity stands right now in the middle of 2026. Our only working instrument in interstellar space is nearly 50 years old, running on a fraction of its original power, and it just did something it was never really designed to do on command, sending back a reading nobody can fully explain yet. Not because anyone went looking for it, because the spacecraft turned, almost by accident, at exactly the right moment, in exactly the right direction, and briefly showed us something a decade of steady, fixed-angle data never revealed. Whether this ends up being a new dimension of already suspected turbulence, or something smaller and stranger. Sitting directly in Voyager 1's path, the only way to actually find out is to keep listening, and to keep carefully asking a dying spacecraft to turn just a little further before its power finally runs out for good. Every major discovery this mission has produced over the past decade, the turbulent structure of interstellar plasma, the surprising magnetic link between our solar system and the galaxy beyond it, the persistent unexplained hum, all came from a spacecraft holding perfectly still, quietly recording whatever drifted past. Nobody expected the next real clue might come not from what Voyager 1 was watching, but from the simple, careful act of turning it a few degrees away from where it had been fixed for 50 straight years. It's a reminder that even with a machine this old and this limited, there are still angles nobody has looked from yet. Still questions that only surface when somebody is willing to risk moving something that hasn't moved in decades. JPL hasn't said when the next attempt will happen, and they've made no promises that it will happen at all. Every additional roll spends fuel and risk on a machine that can never be repaired or brought home. But the fact that a team managing a 50-year-old spacecraft on a shrinking power budget is even willing to gamble part of its remaining life chasing this down tells you everything about how seriously it's being taken behind closed doors, even while the public statements stay careful, measured, and deliberately non-committal. If stories like this are what brings you here, subscribe and turn on notifications, because we're going deeper into the edges of what science actually knows very soon. Drop a comment with your own theory on what Voyager just picked up, and share this with someone who needs to see it, because a 50-year-old machine just handed us a question nobody can answer yet, and that deserves a lot more attention than the silence it's currently getting. Every year Voyager 1 keeps transmitting his borrowed time on a mission that was technically supposed to end more than 4 decades ago, and every strange reading it sends home from here on out could be one of the very last of its kind. That's the real reason this brief, quiet anomaly matters as much as it does, not because it's guaranteed to rewrite physics, but because it's proof that even a dying, decades-old machine, nudged just a few careful degrees off course, can still show us something we didn't know we needed to see.